Hello everyone, and welcome to the NANOG design session. In this session, we will be talking about how to design a multi-tenant data center using EVPN IRB. My name is Ahmed Abir. I am at EME in Cisco, and I have with me Neeraj Malhotra. He is the principal engineer at Cisco and one of the main architect for EVPN technology. So let's begin. The situation is that SDN is trying to achieve end-to-end operational simplicity and programmability across multiple domains such as layer 2, layer 3, SP-WAN, and data center. In your data center, you want to be able to place your virtual workloads and virtual functions anywhere. You want to be able to place and move anywhere. But however, the complication is that the network have across multiple domains have become very complicated with these joint technologies. For example, you are using different technologies for layer 2 and layer 3 networks. Similarly, we have different technologies for SP and data centers, which totally impedes the goal of SDN of operational simplicity. Specifically, in your legacy switch data centers, it was never designed for virtual workloads and flexibility, which means you cannot provision your workloads or spawn anywhere or moved anywhere. On top of it, the legacy data center is basically based on flood and learn, which is highly suboptimal and doesn't give the control of your network, which means you cannot achieve the programmability in your network. So the implication is that with the set of these complex technologies, which were initially designed for the physical compute, it is extremely challenging to achieve the operating simplicity, across SP and data center, and you simply cannot, spawn or move your workloads anywhere. So solution which we are going to present today is a data center architecture based on layer 3 routed fabric underlay combined with layer 2, layer 3 VPN based on EVPN IRB control plane and distributed routing architecture. I hope by the end of this presentation, we will generate enough interest in you that you will take a next step and learn more about this technology. In fact, try this solution and perhaps start the small data center and extend horizontally as your demand grows. We also hope that you would recognize the benefits of using this highly optimized data center fabric with unified control plane across layer 2, layer 3, WAN, and data center that in turns enable the operational simplicity in your network, which we are trying to achieve here. So with that, let's take a look at the objective of the data center architecture. So the first objective is basically we are trying to achieve a unified control plane across multiple domains, such as service provider and data centers, to have operational simplicity. To be able to basically, the other objective is to be able to move our virtual workloads and virtual functions within the data center and across data centers. Eliminate the flood and learn from the network so that we can efficiently utilize our bandwidth using ECMP. Data center must support the network resiliency using fast reroute and fast convergence. We should be able to scale up horizontally as our workload demands and function goes up. Data center must support the multi-tenancy with the layer 2, layer 3 VPN, and it must interwork with the legacy technologies like layer 2 VPN and layer 3 VPN. So just to summarize, data center architecture must be seamless and programmable and act like a big switch or a router, where workloads can be placed anywhere, can be moved anywhere, any host can talk to any host in layer 2 domain, any host can talk to any host in layer 3 domain. They can be basically scaled up horizontally as your demand goes up, as your scale goes up with your, more tenants you have, more workloads you have more functions. But there might be questions, why we cannot achieve all those objectives with the existing technology, like VPLS. First of all, VPLS is the layer 2 technology only. You cannot achieve the unified control plane across multiple domains, which is very critical for your operational simplicity. VPLS do not support all active multi-homing, which means you cannot basically get deeper flow ECMP load balancing. And last but not least, VPLS basically based on the flood and learn MAC learning, which is highly suboptimal, and you cannot achieve the programmability in your network because it doesn't give you any control. With that, I will hand over the solution details to my partner, and basically he will dive into it and explain you the solution.
Thanks, Ahmed, for setting up the context, and good afternoon, folks. Many thanks for being here. So before we dive into the solution, I just wanted to say a couple of things on EVPN. EVPN as a technology is a technology across multiple market segments. I mean, broadly, it has use cases across carrier Ethernet, service provider, layer 2, layer 3 VPN services, as well as in the data center. So in the talk today, we focus specifically on the data center use case of EVPN. And while EVPN is one of the key foundational elements of this data center architecture, and we'll go into great detail with respect to the EVPN technology, I just wanted to kind of emphasize that there are additional elements to this architecture of how we sort of bring EVPN and use EVPN in the data center. So with that, let's dive into the solution. So we'll talk about the solution in sort of 4 key parts. There's the underlay routed fabric, which is essentially a standard IP routed fabric that provides layer 3 connectivity between different leaves and spine nodes in your data center. So nothing terribly fancy here, just standard routed fabric, but we'll realize the benefits of working on top of a standard routed fabric. A VPN overlay that is going to be enabled using BGP EVPN as the control plane. A VPN routing architecture that is going to be based on distributed routing. And one of the key elements of the architecture, which is the mobility architecture that allows VMs or workloads to move across the data center, which is going to be based on EVPN mobility constructs and Anycast layer 3 gateway. So these are sort of 4 key parts that we'll dive into that together sort of give us an EVPN IRB based data center fabric architecture. So an underlay essentially refers to your transport network, which is just pure, it's a basic IP routed network running any routing protocol and providing layer 3 connectivity between different leaf nodes and spine nodes in the data center fabric. The underlay can be a pure IP routed fabric, or it can be an MPLS fabric or a segment routed fabric, essentially any sort of core routing technology that we're familiar with. The overlay refers to the VPN services that we enable on top of this transport network. And in this architecture, that refers to both layer 2 and layer 3 VPN services that will enable using BGP VPN as the control plane. And in terms of VPN encapsulation, the VPN encapsulation, again, can be MPLS, or it can be any other IP tunnel encapsulation like VXLAN. For the presentation today, we'll use MPLS as an example together with an MPLS-based transport. However, I wanted to mention that the architecture and most of the things that we'll talk about are sort of largely independent of the encapsulation, and will apply to a non-MPLS based data center. So it's really kind of, depending on, whether you're a service provider or what kind of network you have, in some situations it makes sense to have an MPLS based data center. In some situations, it makes, an IP based data center works better for you. So next, we'll dive into some of the key constructs and procedures in EVPN control plane that are leveraged to enable layer 2 and layer 3 VPN services in the data center. An EVI essentially refers to an EVPN instance that is used to stretch a layer 2 domain across multiple leaves in the data center. So really this EVI is kind of equivalent to a MAC VRF on each leaf that is part of that VPN. So the EVI or the MAC VRF for any given VPN overlay or a layer 2 VPN instance would be present only on the leaves that participate in that VPN, and only those leaves would have the corresponding MAC VRF or the EVI configured. Any other leaves in the data center that don't really, or that are not really part of that specific EVPN would not have the corresponding EVI or the MAC VRF present. So now in terms of how does the host connect to this fabric? So a host could simply be single homed via a single link attached to a single leaf in the data center fabric, in which case you do not have the resiliency against link failures, and you do not have the advantage of being able to load balance flows on a per flow basis to that host. Or a host can be multi-homed to 2 or more leaves. So there is no specific limit with respect to the technology. I mean, the host can be multi-homed to several leaves at the same time, using a layer 2 link bundle spread across 2 or more leaves. So when a host is multi-homed using a layer 2 link bundle such as this, each bundle link on individual leaves that are part of that bundle's redundancy group are configured with an Ethernet segment identifier, which is a globally unique identifier, and is configured symmetrically across all the leaves that are part of that bundle's redundancy group. For example, here, if the host is multi-home to 2 leaves, both the leaves will have an ESI value and the exact same globally unique ESI value associated with the bundle interface on the respective leaves. So this ESI construct is one of the key multi-homing constructs in EVPN that, as we'll see in some of the upcoming slides, enables a lot of the advanced multi-homing features that EVPN brings in, such as all-active load balancing, fast convergence on failures, and duplicate traffic avoidance. So now, if an EVPN instance is stretched across multiple leaves in the data center, which means you have a layer 2 VPN overlay that stretches the layer 2 across multiple leaves in the data center, then the MACs in that EVPN, all the MACs must be advertised to all the other leaves that are part of that EVPN instance and installed in the corresponding MAC VRFs on all of those leaves that are part of that EVPN instance. Similarly, the host IP also must be advertised to all the leaves that are part of the layer 3 VPN instance in the data center. So this is accomplished via an EVPN MAC plus IP route, route type 2, which is essentially a route that carries both MAC and IP route advertisement to all the other leaves in the overlay. So locally, for the hosts that are locally attached to you, you learn the MACs of the host via hardware learning in data plane. You learn IP to MAC bindings for the host via ND or IPv6 ND or ARP cache And this information of MAC learning and IP learning is combined and put together into a single MAC plus IP route that is advertised to all the other leaves in the overlay. So this is really like two routes packed in one. It is advertising MAC reachability to all the leaves that are part of the MAC or the layer 2 VPN overlay, along with the layer 2 VPN encapsulation information and the corresponding route targets for import into the MAC VRF. And it is advertising IP reachability to all the other leaves that are part of the layer 3 VPN overlay, along with the layer 3 VPN encapsulation, which could again be an MPLS label, a VXLAN VNI, or any other segment identifier, along with the route targets for that enable import of this route into the respective IP VRFs on individual leaves. So now, if a host is multi-homed to 2 or more leaves, it is possible that that host's MAC and MAC IP might only be learned on one of the leaves because of the way the layer 2 link bundle hashes the traffic. And if that host is only learned on one of the leaves, that host's MAC IP route would only be advertised by one of the leaves to all the other leaves in the overlay. However, we must ensure that all the remote leaves are able to load balance the traffic flows destined to that host across all the leaves that that host is multi-homed to. So even if the host is only advertised by one PE router or a one leaf router here. So how do we accomplish that? That is accomplished via an EVPN procedure commonly referred to as aliasing. So what it is essentially each leaf that has an Ethernet segment configured in an EVPN service or an EVPN service enabled on that Ethernet segment advertises reachability to that Ethernet segment in the context of the EVPN to all the other leaves that are part of that EVPN. So for example here, if the host is multi-home to 2 leaves via ESI1, both the leaves will advertise reachability to ESI1 in the context of each EVPN that is enabled on that Ethernet segment. So by doing this, all the remote leaves that are part of that EVPN know the ECMP reachability to a given ESI. And the max reachability is not derived from the PE router or the advertising leaf router, but essentially we derive the MAC reachability from the ESI that MAC belongs to. So by adding this indirection in forwarding between the MAC and the ESI's sort of path or forwarding encapsulation information, we're able to accomplish ECMP load balancing for all MAC-bridged traffic. So now, if there is a failure on the ESI for a multi-homed host, we must be able to converge fast in a manner that is independent of the scale of the MACs that are impacted, as well as in a manner that is independent of the scale of the services or VLANs that are impacted by that failure. So this is accomplished via a mass withdrawal mechanism in EVPN, which is essentially each leaf advertises, in addition to what we saw with aliasing, where each leaf advertises ESI reachability within the EVI context, each leaf also advertises attached ESI's reachability at a global level across all EVPN instances to all the leaves via a single route, which is again defined as an EVPN route type 1, Ethernet auto discovery route. So this is basically a single route that is signaling reachability to a given Ethernet segment across all the EVPN instances or EVPN overlays in the data center. So when there is a failure, by just withdrawal of the single route, the leaf is able to signal to all the remote leaves that it no longer has reachability to the ESI. And this way, the remote leaves via how they program the forwarding plane with an indirection via ESI are able to fix up the forwarding information in a manner that is independent of the scale of the max or even possibly the scale of the services that are impacted. Now, if there is a multi-destination packet from the host, that packet, like a broadcast packet or unknown unicast layer 2 packet or a multicast packet, that bump traffic needs to be flooded to all the remote leaves that are part of an EVPN overlay. So this would include basically for hosts that are multi-homed across multiple leaves. This means that all the leaves that a host is multi-homed to would receive a copy of any replicated traffic or flooded traffic from the remote host. At the same time, we must make sure that for multi-homed hosts, only one of the leaf forwards traffic towards that leaf in order to avoid duplicate traffic. So this is accomplished via a designated forwarder election mechanism, which is essentially the goal of this is that for each ESI that is multi-homed across multiple leaves, we elect one of the leaves as a designated forwarder on a per service basis. So this way, essentially, if you have multiple VLANs or multiple services on that Ethernet segment, you can kind of load balance or load share, rather, the load across multiple leaves. So how does this work? Essentially, all the leaves that are part of an ESI's redundancy group discover each other via an Ethernet segment route type 4. And once each leaf knows about all the other leaves that it shares that ESI with, they all run a DF election algorithm. And at the end of running that DF election algorithm locally, each leaf has a consistent view of which among all the leaves in the redundancy group is a designated forwarder for each service or each VLAN that is enabled on that Ethernet segment identifier. So, of course, only once the DF election is set up, it's programmed, only the DF forwards multi-destination traffic for that VLAN or for that EVPN instance towards the host, and any other non-DF would simply drop it. So now, when a host is multi-homed and originates a multi-destination traffic, like we saw, the traffic is replicated to all the other leaves that are part of the VPN overlay. And if a host is multi-homed, this would include the other leaves that are also part of the redundancy group or that the host is multi-homed to. At the same time, we must ensure that the other leaf that this host is multi-homed to and receives the packet back does not echo the packet back to the host that originated the packet in the first place. And this is accomplished via a split horizon group filtering mechanism, where each leaf for a local ESI that is attached to that leaf allocates a split horizon group label and advertises it to all the other leaves in that ESI's redundancy group. For example, here, for an ESI that is multi-home to leaf 1 and leaf 2 would have allocated an ESI label or a split horizon group label for ESI 1 and advertised that label to leaf 1. Now, leaf 1, when it receives a multi-destination packet that it has to flood on the fabric on ESI 1, it will impose this extra label or this additional split horizon group label on the packet when it replicates the packet towards leaf 2. Now, leaf 2, when it receives the packet with this additional split horizon group label that it allocated for its local ESI 1, it knows via that label that the packet originated on ESI 1 and it must not put the packet back on ESI 1. So it will still flood the packet on all the other ports in the layer 2 bridge. However, it will skip putting the packet back on ESI 1. So now coming to host mobility. Right, so I mean, one of the key goals of this architecture is to be able to place and move your workloads across your EVPN instance or the VPN overlay in the data center. So if a host moves from one leaf to, say, another leaf, then all the leaves that are part of the EVPN instance in the data center must be able to unambiguously determine what the current reachability information for that host is. So this is accomplished via sort of a route versioning mechanism, which is basically a sequence number attribute that is associated with each MAC plus IP route type 2. When a host is learned for the very first time, its MAC and IP route, route type 2 is advertised without any sequence number attribute attached, and the sequence number is implicitly assumed to be 0. Now, when the host, let's say, moves here from leaf 1 to leaf 3, and leaf 3 learns the host locally, again via ARP learning or via MAC learning, leaf 3 at this time already has an existing route that was advertised by leaf 1 for this host. So based on that, leaf 3 will bump up the route version or the sequence number associated with this route when it advertises the route type 2 or the MAC IP route for that host via itself or with itself as the next hop. So when all the other leaves receive this route from leaf 3 with a higher sequence number, they know that this is a more recent reachability information, and they will modify the forwarding state for the MAC for this host essentially to essentially recurse via leaf 3 instead of leaf 1. And leaf 1, when it receives this route from leaf 3, can use this advertisement to clean up any stale state that it might have learned or that it learned, that it would have learned for that host locally prior to the move. So next, we'll compare or look at how to do routing, inter-subnet routing in this architecture. So we'll go over sort of three routing architectures that are possible with this: centralized routing, distributed routing with asymmetric IRB, and distributed routing and with symmetric IRB. And we'll kind of draw some comparisons and try to show why for this architecture we prefer one over the other. So centralized routing, this is more of a traditional routing architecture in a switch data center, or rather mimics more of a traditional routing architecture in a switch data center, where your data center predominantly is a layer 2 fabric. It's predominantly, most of the devices are layer 2 devices, and all the leaves are pure layer 2 gateways. And any inter-subnet traffic that has to be routed across subnets or across VLANs is routed on a centralized gateway. So what this means is that all the layer 2s within your data center have to be stretched all the way to the centralized gateway. So the centralized gateway can do integrated routing and bridging and route inter-subnet traffic. So this implies that the centralized gateway has to maintain ARP state or ND state for all the hosts across all the VLANs or subnets that it is a first hop gateway or a centralized gateway for. So this obviously presents somewhat of a scale challenge in terms of scale, where just because of the sort of, you're limited by the ARP or the adjacency scales on that centralized gateway. And once you kind of hit the capacity, you cannot just easily increase the capacity of your data center, particularly the routing capacity, without upgrading that centralized gateway. In addition, it also arguably presents a single point of failure. So the key difference with distributed routing is that your layer 2, layer 3 boundary is pushed down all the way to the leaf. So there's no longer any centralized gateway. Instead, the routing functionality is distributed across all the leaves that are part of the layer 2 or that EVPN instance. So essentially, what this means is that I mean, basically, you have a distributed routing gateway that is spread across all the leaves within the EVPN instance. The asymmetric nature of this architecture refers to the fact that the packet on the ingress leaf, which is the first hop gateway in this case, is routed directly to the destination VM's MAC. So when the ingress leaf routes the packet, it encapsulates the packet with the MAC rewrite with the destination MAC as the destination VM's MAC. So it is routed there and then forwarded, or IRB forwarded via a MAC lookup towards the egress leaf. And then on the egress leaf, it is simply bridged based on the MAC lookup towards the destination VM because the packet is already encapsulated with the destination VM's MAC. So this again, it's a little bit better in terms of scale as compared to centralized routing, since the routing function is distributed across multiple leaves. However, it is still somewhat of a scale challenge because the ingress leaf still needs to maintain ARP adjacencies or ARP entries or ND entries for all the remote hosts in a stretched VPN overlay or an EVPN instance. So now the key difference with symmetric IRB is that the ingress leaf no longer maintains any ARP state for a remote host. So only ARP entries or ND entries and direct adjacencies are only maintained for directly connected hosts that are local to that leaf. And for all the remote hosts that in the EVPN overlay, the ARP entry is replaced by a routing entry that is installed directly into the IPVRF based on the MAC plus IP route type 2 advertisement from the egress leaf. So another way of looking at it is basically instead of installing an ARP entry for a remote host in a stretched subnet or a stretched VPN overlay, I put a much like an L3 VPN style routing entry directly into the IPVRF that recurses over the egress leaf, which looks like a remote PE router to me, and together with the VPN, L3 VPN encapsulation or L3 VPN label advertised from that remote leaf. So by doing this, essentially, we're able to improve the scale significantly where you're no longer limited by adjacency or ARP scales on your top of rack or leaf switches, which would typically be, a lower scale as compared to, say, a routing scale or a VPN routing scale supported on the leaf. So by doing this, we're able to scale much better, and as your workloads or your tenants in the data center increase, you can simply scale the data center design horizontally much easier. So now the next question is that once we have this distributed gateway, how do we enable hosts to be able to move across a stretched layer 2 EVPN instance seamlessly while maintaining its runtime state? So once again, sort of coming back to mobility, which is one of the key things that this is trying to accomplish, we want the hosts to be able to move, and not just move, we want live migration, right? We want hosts to be able to move while keeping their runtime state, which includes their runtime ARP cache, and it includes an ARP entry for their default or first hop gateway. So this is accomplished by making this distributed gateway an Anycast gateway. Essentially, all the leaves that are part of a distributed gateway or first hop gateway for a given subnet are configured with the exact same MAC and IP for the default gateway. So essentially, you can look at it from the host point of view. The gateway for a subnet, for a given subnet or a given VLAN never changes. You still have the same IP, gateway IP and gateway MAC, and if a host has an ARP entry for its default gateway, it can simply move while maintaining that ARP entry. And if it moves to another leaf, that leaf also is part of the same Anycast gateway, and you truly have a distributed Anycast gateway across your data center fabric. So next, just to get a feel for how it comes together, I just picked one flow to see how the control plane and the data plane comes together for an inter-subnet packet flow. So there are a lot of kind of packet flows and failure flows, of course, we could go through and spend a lot of time. I just picked one specific flow for an inter-subnet routed packet to see how the control plane is established and how the data plane works. So let's say we have two subnets in the fabric. We have an orange subnet and a blue subnet. There is VMA in the orange subnet that is sitting behind leaf 1, and there is VMB in the blue subnet that is sitting behind leaf 4. And VMA originates an inter-subnet packet that is destined for VMB's IP in the blue subnet. The packet would be sent to VMA's first hop or default gateway, which is the ingress leaf 1 in this case. The ingress leaf would do an IP lookup in the IPVRF. And in this case, I just picked an example where the destination blue subnet is also local to leaf 1. It doesn't necessarily have to be local. It could not be. It may not be. But in this example, it just so happens that the blue subnet is also local on leaf 1. So because the destination subnet for that IP is a local subnet on leaf 1, leaf 1 will generate an ARP request for the destination's MAC, which is VMB's MAC. The ARP will be flooded across your data center fabric to all the other leaves that are part of the layer 2 VPN or the EVPN overlay. Each leaf will flood that packet on the local port or local ports in that layer 2 service, including leaf 4, which will flood the ARP request on its local port towards VMB. When VMB gets the packet, VMB will generate an ARP reply. However, now the ARP reply would be destined to the Anycast gateway's MAC. So because the ARP request was originated from a default or an Anycast default gateway, the unicast ARP reply would be destined to the Anycast gateway MAC. And because this Anycast gateway is distributed across all the leaves in that EVPN instance, the ARP reply will be consumed locally on leaf 4 itself, because it is destined to leaf 4's local MAC as well. So leaf 4 will simply learn the local MAC IP of VMB, install it in its ARP table, install it in its routing table, and generate a route type 2, which is a MAC plus IP route advertisement in EVPN control plane to all the other leaves that are part of the layer 2 VPN and the layer 3 VPN overlay in the data center. So based on this route, all the remote leaves that are part of the layer 2 VPN overlay, or rather the EVPN overlay, will install VMB's MAC entry in their MAC VRF. And all the leaves that are part of the layer 3 VPN overlay will install the IP entry for VMB in their IPVRF, pointing to leaf 4 as the next hop PE router. So once these entries are installed, essentially now any inter-subnet packet destined to VMB's IP will again go through an IPVRF lookup on the ingress leaf. This time ingress leaf will find an IP entry for that VMB's IP that was installed based on the route type 2 advertisement from leaf 4, and route the packet to leaf 4's next hop. The VPN encapsulation, much like layer 3 VPNs work, will terminate on leaf 4. Leaf 4 will do an IP lookup, find an ARP learned entry for VMB, and route the packet to VMB. So this is where the symmetric term sort of comes from. Symmetric IRB term comes from the fact that the packet gets routed on the ingress leaf and routed on the egress leaf. Similarly, any bridge traffic, intra-subnet traffic, would hit the ingress leaf, go through a MAC VRF lookup for the destination VMB's MAC, And based on that MAC lookup, it will get forwarded to the next hop, leaf 4. Leaf 4 will do another MAC lookup and bridge the traffic towards, on the port towards VMB. So now to summarize, basically what we achieved is a unified control plane in BGP EVPN across both layer 2 and layer 3 within the data center. And now this is where I kind of want to mention that EVPN is indeed a technology for layer 2 and layer 3 VPN services in the service provider core as well, right? So by bringing EVPN into the data center, you truly have an opportunity to achieve sort of a single VPN control plane across layer 2, across layer 3, across the data center, and across the SP-WAN. So that itself is a compelling sort of proposition in terms of the kind of operational simplicity that it enables. By being able to stretch the EVPN or layer 2 VPN anywhere within the data center, or even, we didn't talk a lot about data center interconnects in this, but possibly even across data centers. By being able to stretch the layer 2, you have the flexibility to place your workloads anywhere in the data center. You have the ability to move your workloads with live migration across anywhere across the layer 2 overlay. Now, the next point, by eliminating flood and learn, and by bringing in ECMP both in the overlay and in the underlay. So overlay VPN, ECMP that it's enabling both for MAC and IP routed traffic, as well as your underlay fabric being a standard IP routed fabric, you have ECMP semantics, both ECMP load balancing per flow, both in the overlay and in the underlay. You really achieve a highly optimal network fabric or a data center fabric where you can sort of aim to really utilize your network resources to the maximum. Depending on what kind of underlay fabric you deploy, whether it's a standard IP or MPLS fabric or potentially a segment routed fabric, you have additional capabilities in your underlay, such as traffic steering, ECMP we already talked about, as well as fast reroute kind of features. With distributed symmetric IRB, we're able to scale the data center horizontally up as your data center needs increase. Multi-tenancy with both layer 2 and layer 3 VPNs enabled in the data center. And this last point about interworking with legacy L2 VPN and L3 VPN technologies, we didn't really have the bandwidth to get into that topic in much detail in this presentation, but I just wanted to at least mention that it is a technology that interworks with legacy L3 VPNs and legacy L2 VPNs such as VPLS. So with that, thanks very much, and I would like to open it up for any questions.
Hi, Teddy Vandenberg with IBM Software. I'm wondering if the summarized, or the symmetric IRB, it sounds like a good solution. I'm always looking to get more gateway access for any sort of layer 2 extension. But it looks like it would have a pretty big impact on routing tables because you're doing far less route summarization. So how might that scale and how might that impact your horizontal scaling?
So you mean the VPN routing table on the leaves?
Yes.
So you're concerned about that your leaves have to be capable of VPN routing sorry, could you repeat exactly what is your concern?
I'm possibly mistaken, so feel free to
Sure.
check me out. But if you're taking what would have been previously summarized routes and now you're just dealing with 32s on the network, so you have a large increase in your routing table size.
Got it. Yeah, so yeah, I get the question. So so basically, like if you're just doing north-south routing, right, you can live with summarized routes. So that's the bottom line. I mean, the moment you stretch your layer 2 across multiple leaves, you no longer have the ability to do east-west routing within the data center using summarized routes. So there's really sort of no way around that. I mean, once you have the layer 2 stretched or the VLAN stretched across multiple domains, especially to achieve optimal routing, where you can ensure that your route is, or the destination is always just one hop away in a traditional sort of spinal leaf topology, then you do need to install the /32 routes. So yeah, I mean, in terms of the scale, there is that's where we achieve somewhat better scale, or in fact significantly better scale by not installing ARP entries, but instead of installing ARP entries, we install like a layer 3 VPN route for that /32, which scales much better than the ARP scale. And I mean, even with merchant silicon, you do have at least the routing capabilities are in at least a couple of million routes on the TORs.
Okay, thanks.
I think that's about all the time we have for questions, so thank you very much.
Sure. Thank you.